Okay, hello, welcome back. Welcome back to another one of my video log recording sessions where I talk about genetic algorithms. The date is 2025, April 30th, and today I'm going to talk about how to start caring for individual entities. Well, not directly caring, but making sure that individual entities on an individual level or an individual basis improve or are given the chance to improve. And yeah, let's start. So, in my last video, if I remember correctly, I left off saying that, two things. There was two videos. There was the last video, and then there was an appendix to that. In the first one that I just mentioned right now, I've stated that it is quite sad that entities don't seem to improve over time, as can be seen here, as there's some utility history just keeps going down. And I don't think that's a good sign. I know I usually say that whether an entity is good or bad is not an easy thing to decipher. However, because the problem space can change and since you don't know what is good or bad, you won't be able to know what is better or worse or what is best or worst. However, in this case, where entities, these are the entities that were struck out because they went over the threshold, and when most of the entities show a general downward slope, such as these plots, and none of them actually go up. None of the slopes ever go up. Well, some do, but in this case. But overall, they start off somewhere high, and then they almost always end up somewhere low. And the reason for that was that in order to go up, the entities were solely depending on mutation, and there wasn't a mutation which is actually a macro level. It's not on an individual or a micro level. And when you are actually this high up, for example, when you're actually this high up, there isn't a lot of room for you to mutate upwards. And even if you do, it is very likely that your summed constraint value will go above the threshold and you'll be struck out. So I wasn't actually giving the entities anything close to a chance, any kind of opportunity whatsoever for them to learn, or adapt. Learn or adapt. And in the way that procreation, of course, you might say, oh, there was procreation, but there was procreation, but this is for the entire population. This is the way for the entire population to improve, not for individuals. Not for individuals, but entire population. So this is on a collective level, procreation, and so was mutation. But when only these two are provided, individuals rarely ever improve over time or over generations. So that's a bad thing. That I can say is an objectively bad thing. And when you have so many entities being limited out of the population because they were ranked so low, because the way it goes, if I were to remind anyone, is that the way it goes, the newborns will be put in front of the list, and the pre-existing world would be back here, and then the population limiter would work something like this to keep the world at max population. So naturally, because the world was previously ordered, these entities who are kind of destined to be left out, limited out, are low in some utility values. So that's also one thing to address, one issue to address. This looks like a United Arab Emirates. So coming back to the first Jupyter notebook that I modified is this Track Evo 1, and I kept the overall structure of the procedures or the notebook as almost the same, exactly the same as Track Evo 0. And what I did instead in this, or rather what I started doing, was I shuffled the world before I limit the population. So when I shuffle it, so the newborns would be added in front, and the old ones would still be here. But then I shuffle it. Right after I let the mutation happen, and I let the selector function work, and then I shuffle it. So what happens is from this, after the selector has done its work, this becomes something like this. And then the limiter will do its work. So not all newborns are guaranteed to survive onto the next generation, but some old pre-existing, or rather more specifically, entities that had low summed utility value would also survive. And what that does is, and if you remember, the purpose of this, that which I added in my appendix to the last video, was that I had a look at the lifespans of these entities, and the average age for the entities that were left in the final state of the world was 27. So let's write that there. Let's come here, and world 27 limited is something, and struck out was 27, and then for the struck out entities it was 7.35, 7.35, and no, and the limited entities was 39.53. So 39.53. So that was in track eval. Oops. Track eval 0. Track eval 0. And what I did in track eval 1 is I shuffle the world, as you can see. Where is it? As you can see here, I shuffle the world, and then I let the pop limit do its work. And then what that does is, in terms of entity distribution, it does bring about some change in the shape of the distribution. As you can see here, it went from this to this, so it's more of a, this used to be kind of skewed, but this is more of a bell-shaped normal curve. So that's one thing. However, so you might say, oh, then maybe, one might say maybe the average peak and the average plateau level decreased by some amount, and that is true, but not by a whole lot, because the average peak was 1407, and then it went down to 1385, and then the average plateau was 1343. No, average plateau was 1362, and then it went down to 1343. So it's not by a whole lot, and we still do get the maximum ever at 1535 or 1540. So in this case, by shuffling, I remember that I quite consistently kept getting 1540, which is, as far as I know, the best combination so far. The best of the best, the highest it can be, given all these utility values, constraint values, and the max constraint. And the plots look like this, so nothing that, not much different. And the oldest entity lived for 234 generations, and then the oldest entity in the previous one, whereas it was 164. So I'm talking about the oldest entity in the world. So quite a bit, quite a bit of a difference there. And if I go on to have a look at the average age, it was, for the average age for the entities in the final state of the world, in the final world, was 38. So I'm gonna copy that, and then it's 38. And then for the struck outs, it was 7.35. No, I got that wrong. It was, for the struck out, it is 6.75. 6.75. And for the limited, it is that right? 37.82. 37.82. So you can see that this increased, this did not increase the average lifespan, and this didn't increase. So shuffling the world, shuffle world will increase the lifespan of entities that remain until the very end. least that's what happens for now. And it doesn't harm the overall plateau or peaks, or the overall average level of plateaus or peaks. Yeah, and here's the distribution of average lifespan from track evo 0, so from the previous video. And here's a the same thing, but now you see that it is more skewed to the right. Same for struck out, same for world. So shuffling does do some work, but only this. It only increases the lifespan in the world only, not for these two. So what I did next is track evo 2 in this notebook. All this notebook, well, let me rephrase that. All I did in this notebook, or for this notebook, and for me to work better, all I did is streamline the procedures. So everything is the same, except that when the evolution iteration is done, I would assess it, and I would do all these calculate age or steps, still part of the assessment, and then I'd have the JSONs and the plots saved in the final part, in the last bits of the notebook. And to do this, I had to instantiate these two lists. So these are limited lists, and this is the limited list, and this is the struck out list. And I also made I had to make some changes to the to the selector function and the pop limit function, so that when something is either struck out or limited out of the population, these two functions would take out that entity and take out those entities from the world, which is a list, and put it into another world, put it into the according list, which is either the limited list or the struck out list. Apart from that, it's the same, and by putting all this saving JSONs and saving all the JSONs that were struck out or limited part towards the very end, by putting those off towards the very end here, the evolution only took 16 seconds when compared to 21 or 22 seconds. And even in this notebook, I also applied the shuffle to the world, and what that does is this, so basically it's the same thing as you can see here. This distribution and this distribution, you could say they're the same, almost the same. And see, it doesn't even harm the average peak and the average plateau level that much. So that's what happened in track evo 2. And in track evo 3, now this is where I did something more interesting for the individual entities. I made a function called learn from others. So I know it's bad naming, but that's what I did. And basically it looks something like this. For every entity that is put in the or applied to a loop, what happens sorry, excuse me. Alright, I'm back. Sorry about the awkward silence. I had to get some water. So, for every entity that is in the list, which is in the loop, an entity will be passed into this function and the world, and a learn rate, not to be confused with the learning rate from other neural networks. Learn rate is set, and the entity in question will learn from one of the top something percent entities. We'll just choose an entity that is amongst the top entities, amongst a certain top percentage of the world, and it will calculate the difference between its chromosome and the other's chromosome, and so when the entity difference is calculated, and for every gene that is different, the entity in question, ENTT, will try to flip that gene. Will try to either activate it or deactivate it in order to mimic what the in quotes better entity is doing or has done. So if the learn rate is 0.3 and the entity in question had a 0 in that place, and the other entity from the top 10%, for example, had a 1 in the same place, with given a 30% chance, the entity in question will try to make that 1 into a 0 or 0 into a 1, either way. And so the entity difference, the list, is something like 1 where things are different, where a gene is different between the two entities, or 0 where the gene between the two, where the gene in the same place between the two entities are the same. So wherever there is a 1 or true, it will try to decide whether to imitate or not, given this rate. So right now it's a 30% chance of succeeding in copying it, or a 70% 70% chance in copying it. And one thing that I should mention is that I did a lot of I ran this a lot without knowing that initially the code was something like this. So many of the runs that I did was actually just me running this function that would actually do nothing, because all I was doing was just comparing it, and of course it would be false because I'm doing this computation. Something is not 1 minus something. It would always be different when all we're talking about is either a 0 or 1. 1 minus 0 is 1 minus 0 is 1, when the original gene would be 0, or 1 minus 1 is a 0 when the original gene is a 1. So all that time I was getting a false, the value of false for this line, and it wasn't doing anything to the entity in question, so I fixed that. So that's what I started doing in this notebook, that is TrackEvo 3. You can see the function name, learn from others. And what this does is ultimately, I would like to go through everything I did, but that's just too much. But ultimately what that does is it moves the entire population. It shapes the entire population into a something of a normal, well, a lot like a normal curve, normal distribution curve. But it also shifts it to the right, towards the higher end. Now compare this. If you compare this to this one, these are very two stark differences. See here. You'll see that something went over 40. Yeah, 45 or 43 or something. So this is what happens. This is ultimately what happens when you give it the learn function for individual entities to actually learn from top something percent. And well, naturally, when that happens, it is quite natural that the average peak level also rises to 1419, and the average plateau level also rises to 1388 compared to 1349 and 1399. So this is quite good. This is definitely good, because now I'm somewhat guaranteeing that the entities don't just deteriorate and die. Entities now can, on an individual level, can improve. Mutation is not the only source of improvement anymore. But the more interesting thing here is that when I have a look at the lifespans, I still shuffle, by the way. I still shuffle the world. But when I do shuffle. Yeah. Let me just check something. Nope, not there. Go away. I'll cover this in a later video, but it also turned out that adding newborns to the world first and then letting the entities learn is better. And yeah, I should definitely cover it. And the way I came to that conclusion is not in this, is it? Oh, I don't know. Is not something that I'm going to talk about in this specific notebook, but it turns out that that's better. Adding the newborns and then letting the entities learn and then shuffling it and then limiting the population, because that's the order of things that were done here. And when I do that, the average lifespan for entities in the final world was 37.978. .978 was it? Yep. And for the struck out, it is 29.27. So a huge 29. What was it? I keep forgetting. 27. And for the limited, it is 37.01. 37.01. So a huge increase. A huge increase there. This is when entities are allowed to learn. Oh my god, this is so annoying. So this is when entities are allowed to learn, and already I can see a huge increase in the lifespan for the struck out entities. It went from somewhere at 6 or 7 all the way to 29. And well, but a more stark difference can be seen in the plots, as I'll show you. This is one, well, these are the plots when learning was not applied for the individual entities. See all the slopes going down. Very depressing. But for the same limited entities, for the entities that were still, regardless, eventually limited out of the population, this is what happened. They're not that downward sloping anymore. They still do try to fight their way back up. So these are, on the left is when the entity, on the left, this is when the entities were not given the chance to learn, and they withered out of existence by limitation, by population limit, except this one. But this only happens when the entity was introduced into the evolution at a very early generation. For example, generation 1, which is the second generation, and then it lived for about 60 something generations. But apart from this, see, this is very lucky. Apart from that, when you start high, you come, the only way is down. So things are very, very, sad, depressing. However, on the right, on this one, you'll see that even when an entity starts high, it will come back up to some degree. Not this one, but yeah, it will come back up. See, now it's a lot more common that entities, well, this one was kind of unlucky, but even when this entity was this unlucky, it still fought its way back up. Of course, it started this high, but it ended this low. But at least it's not going all the way down, like diagonally down. Now, this is, when I say learn, I let the entities that were at the, what was it? I only applied the learn function for entities that were, where is it? That was like the bottom 30%. So if this was the world, current world, this is exactly half, and I shouldn't do that. This is the top 30%. Well, let's just say top third, mid third, and bottom third. Actually, no. Let's just say this is 50, this is 75, and this is high, some utility scores, and this is low. So I let the bottom 30%. So this is 25%. So I let about this much learn from 50, 1, 2, 3, 4, 5, from this much. So these guys would learn from these guys. That's what happened. So if you are just stuck somewhere in between, well, tough luck. At least in these scenarios that I've done today, these entities were not learning from the top entity. So that's another thing that I could do a grid search on. There would be the world, and I can decide. Well, what can I decide? I can decide who gets to learn or not. So it could be either from 0, because right for now, you know, suppose there were 10, well, not 10,000, 1,000 entities in the world. I could let all entities, learn. I could have the bottom half learn. I could have the bottom 30% learn. Or I could have the mid, 500 entities learn, etc. So I can do that, and I could also change the learning rate, not learning rate. It's I named it learn rate. I know it sounds, it is hard to say, learn rate. And I could do that from 0.1 all the way to 1, which is 100%. 0.1 being 10%. But still, have a look at these plots. For example, look at this one. Well, it's still kind of started early. Let's find something. And again, in a later video, I'm going to talk about a way to assess all these plots, collectively, so that I don't have to go through all of the plots, because there are always tens of thousands of plots to go through, and it's very time consuming. A way to do that, if I want to talk about it right now briefly, is to measure the slopes and average them out per entity, and then average those averages. So it would be an average of averages of slopes, in order to find out if the given some specific parameters, how the evolution turned out to be, whether it actually was good or bad, beneficial or not beneficial, whether a change in the parameters or the change in the order of process or procedures actually did anything. But yeah, now you can see that they're not all downward slopes. See, even this one, this started at generation 2, and it went all the way up here, almost reaching the plateau. Yep. And what else did I want to cover? I cover the age. have a look at the sum utility history for entities in the final world when learning was enabled. See, these are not all downward slopes either, as opposed to these. You'll see that they're all downward slopes, whereas if you look here, they're not that much downward slopes. They do sometimes go down, but we still have these, but we do more often get a lot of these as well. And this is when only the bottom 30% were allowed to learn. So it still proves the point, I think. Oh yeah, one last thing that I should mention is that so far, no matter what I do, the average lifespan for limited entities don't seem to improve. I need to find a way to improve this. Maybe, again, changing the range for which entities get to learn will might work, but so far the average lifespan for the limited entities don't seem to change. Oh yeah. And previously, one last thing, one very interesting, was that when shuffle and learning did not exist, there used to be around 2,000 entities that were struck out, and around 12,000 entities that were limited out of the population. When shuffling and learning is innate, actually, even when shuffling was, when only shuffling was introduced, I still got just about the same number of entities that were struck out and limited. This is still like 12,000. So in total, the number of entities that were either struck out and limited used to be around 20,000. No, 14,000. 14,000. Yeah. But I would have a lot more limited entities. I would have a lot more entities that were limited out of the population. Yeah, but when I have the shuffle and I have the entities, bottom 30% entities learn, it happens. What happens is that the number of entities that are struck out is increased to 5,817, so around 6,000, let's say. And the number of entities that are limited out of the population is 8,100. 8,193. So about, at most, maybe 8,300. Struck out is 5,800. So in total, that's 14,000. Still 14,000. But I have a lot fewer entities that are limited out. Of course, you could say that all the entities that were not limited eventually when to get struck out, because then the math works out, because the total number of entities that were either limited or struck out is still around 14,000, but the number of entities that get limited out of the population decreases by about one third. Yeah, that's about it for now. In the upcoming videos, I'll talk about how to measure the metrics, what metrics that I should use, whether and those might include average lifespan, slopes, average of slopes, averages of slopes. I'm not saying that wrong. It's an average of averages of slopes. Mean of means of slopes, or whatever. What else? What else should I include? Yeah, and do a whole grid search. Yeah, on grid search dependent on the learn rate and what percentage from what point to the start, well, from what point to what point within the world of entities should be given the chance to learn. Yeah, that's about it. Again, I think it's quite funny and sad that I didn't notice, and that I didn't notice that when I made this mistake, when I made this mistake, when I put two equal signs there, and then I thought the genes were getting, imitated, or they were being improved. They weren't, because all this does is give false, give the value false, and then I thought to myself, well, something is changing. It wasn't. Nothing was changing. I was just getting some random results within a range, and I thought that was a sign of improvement. It wasn't. Embarrassing, but funny. I am a terrible programmer. Very, very terrible. So that's about it. Thank you very much. See you next time. Bye.